Okay, so let's talk about bone development. So hopefully you guys are all experts on bones and cartilage, and so we can start to talk about how the two of them meet and what happens when they do. So, first of all, bone development is referred to as ossification. So if anyone talks about ossification, you know what they're talking about, yeah? Now, basically this is a process which starts at different times in the embryo, depending on what kind of bone you're dealing with. And there are two types of bone development that we will be talking about. Now, don't confuse bone development with bone growth. I'm talking about growth. I'm talking about the tissue itself growing, which means we're talking about apositional versus interstitial. And hopefully we all know that apositional is the only type of growth in bone. Whereas bone development specifically refers to the type of development that we're dealing with. So there are two types: intramembranous ossification and endochondral ossification. Let's see if we can just turn down the volume a little bit. Okay, so basically in both cases the result is the same. The result is bone. But depending on what type of bone you're producing, you're going to start a little differently. And so with intramembranous ossification, the bone tissue is actually laid down directly. Okay? So you basically start out with mesenchymal tissue and go directly to bone. Whereas with endochondral ossification, you have, as the name implies, chondro shows up in there. Okay? The name implies there's a cartilage intermediate. Okay? So you start out with mesenchymal tissue, go to cartilage, and then eventually go to bone. So let's talk about intramembranous first. This is the direct bone formation. And by the way, much of what I'm going to be saying today is already on the slides, because in previous years when I teach this in the fall term, there is the question of a long weekend, and the lectures are usually on a Monday, and so I tend to lose one lecture because of Thanksgiving. So my students end up having to learn this stuff on their own in some cases. So that's why there's more text than usual on your slides. So again, intramembranous ossification, basically what we have here is bone developing directly from mesenchyme. It's still a process. It still goes through stages, but it doesn't have any intermediates. You just go directly into bone tissue. Now, it starts relatively early, about the 8th week of gestation. And what you have is basically a process that produces the flat bones of the skull. So basically, your cranium, cranial bones, facial bones, the mandible, these are the flat bones that are going to be produced by intramembranous ossification. Most of the other bones in your body are going to be produced by endochondral ossification. Okay, so they're generally referred to as the long bones. Now, how does this actually start? So I think what I will do is I will switch over to diagrams. You guys can follow along on the slides, but I will basically be drawing this stuff as we're going along. So initially, you're going to start out with mesenchyme cells. And again, mesenchyme cells, as if you recall, are the undifferentiated cells. They have fairly pale staining nucleus and not much cytoplasm around them. They're sometimes referred to as being stellate, or described as being stellate, or star-shaped. And so we have these undifferentiated cells kind of starting to aggregate. Okay? So instead of being well spread out, maybe I should just draw this smaller just to make it easier, so you guys can draw them as little tiny stars if you want. So you've got initially a bunch of mesenchyme cells, again, schematic. Just looking, showing the cytoplasmic processes. So we've got typical mesenchyme tissue. This tissue starts to aggregate. So mesenchyme cells start to aggregate and come together. So we end up with a lot more of these cells closely associated with one another. So you're going to be looking for evidence of this on your slides. You'll be looking for areas that have few cells, and then you're going to be looking for areas that have a lot of cells close together. Now, at some point, these cells start to differentiate into osteoprogenitor cells. That differentiation is not really clearly visible under the light microscope, so you don't have to look for that or be able to distinguish a mesenchyme from an osteoprogenitor cell. But basically, the mesenchyme cells become this more specifically differentiated cell, which is the osteoprogenitor cell, which will eventually become an osteoblast. So once these cells become osteoblasts, we've got, again, more of these cells aggregating one region, and then differentiating into these more filled-in cells. Remember, osteoblasts will tend to be more basophilic in terms of their appearance. Okay, so they start to aggregate. And they start to lay down osteoid. What is osteoid again? What is osteoid? You guys said you knew everything from last week. Didn't get a refresher. Osteoid. Sorry? Exactly. It's the organic component of bone matrix. So they start to lay down osteoid. Now, what is the main component of that? What is the main part of the osteoid? Collagen. Which type? Type 1 collagen. Very good. And which is going to be eosinophilic. Right? So that's why I'm switching to red. Okay, so we're going to have some osteoblasts laying down some osteoid. Now, one of the other things that will have to happen in this region, as this tissue is starting to aggregate, is we will probably start to see more blood vessels in this region as well. So we're going to see some capillaries and venules. We'll learn what they look like in a later lecture. But we're going to start to see the presence of some of these blood vessels. So these are blood vessels. Why do we need these blood vessels? Well, why do we need vascularization? Calcium. Calcification is one of the things that will be happening to this osteoid. You need to bring that in somehow. Calcium is coming in from the bloodstream. Last week I mentioned a friend of mine who lost a tooth when she was pregnant because the calcium was being stripped from her bones. And so the bones, her teeth were weakening when she was pregnant. She had twins. So it's twice as much calcium was required, I guess. Okay, so, again, where's that calcium coming from? It's coming from the mother. It's coming from her bloodstream and being transferred to the fetus. And it's all going in here. So we're going to have blood vessels coming into the area as well, and so that's vascularization that's going to be occurring, and it's going to be a very common feature of this process. Okay, so let's take that down a little bit further. At some point, I'm going to try this first. Small bony structures called spicules are formed. Seems that the term spicule tends to be used when we're looking at a relatively small structure. When it's a little larger, we refer to them as trabeculae. So we have a bone spicule. And that bone spicule will have a layer of osteoblasts on the surface. I'm not going to fill in the osteoblasts, but again, they will be fairly basophilic because they're actively secreting matrix components. Again, type 1 collagen being the main one. Okay, so osteoblasts. And again, over here, we've still got more of these mesenchyme cells aggregating and differentiating into osteoprogenitor cells because they will be needed. And then we still have those blood vessels nearby. So we're going to just keep these two and just redrawing those two. Okay. So let's turn off the diagram for a moment and go back to the slides. So here's what we just described looks like. And staring into a bright light is making me a little blind right now, so I'm having a hard time really seeing the details here. But let me just turn down the lights a little bit. Hopefully that helps you guys at least. Okay. So what we're looking at here is just kind of this irregular arrangement of cells. You can see they're kind of scattered fairly randomly. This is mesenchyme tissue. And this is where everything begins, but it hasn't quite started yet. So all these cells, the mesenchyme cells, all you're really seeing here is the nucleus. And you're kind of seeing these very fine tendrils coming out from each one of these cells. Those are the cytoplasmic processes. Okay? Now, if we go a little bit further in development, we start to see kind of an aggregation. These cells are starting to become a little bit more closely packed together. We have an aggregation of not osteoblasts, but we have an aggregation of mesenchyme cells. They start to differentiate into osteoprogenitor cells, and then start to differentiate into these cells up here. You can see they're fairly tightly packed, and start to become a bit more basophilic, and these are osteoblasts. Okay. Right in between them, you can start to see a little bit of this eosinophilic material being laid down, and that's going to be mostly type 1 collagen. We're seeing the laying down of the osteoid. This vision here is out of focus. It just contains a slightly bigger piece of the osteoid as well. And again, just more osteoblasts around it. Right here, 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 you can clearly see that there are some sections through a couple of blood vessels. Okay, so we've got a blood vessel here, there's one here, there's one actually, you can see some blood inside of it as well. Another blood vessel over here. There's probably more of them within this unfocused region as well. Okay, so you start to see a close association of the blood vessels with this whole process. One of the other things that the blood vessels can bring into the area would be more stem cells, specifically hematopoietic stem cells, cells that can differentiate into cells like monocytes. What is a monocyte likely to differentiate into? There's a couple of cell types that we've already met that a monocyte can differentiate into. Yeah? wedge would be one thing. What's another one? We would have talked about it in lab last week. Where do osteoclasts come from? They would come from the monocyte lineage as well. So you would have monocytes or macrophages kind of fusing together to make this multinucleated cell called an osteoclast. This will become important later. So again, as we progress, we start to see a larger bone spicule or maybe a bone trabecula at this point. Again, depending on which source you go to, you'll have some different terms for this. So you have this bit of bone tissue here. You start to see that we've got some cells embedded within it. So some of these osteoblasts have become embedded within this tissue. You can see actually one of them here becoming embedded. It's in the process of doing that. Here's another one in the process of becoming embedded within the tissue completely. Okay? So they differentiate into osteocytes. Quick quiz. What is this cell connected to? Are osteocytes connected to other things or not? Okay, so they have canaliculi. They're connected to other osteocytes and osteoblasts. Remember, the osteoblasts are out here. They're in close contact with blood vessels, like this one over here. Okay? So what we have here is osteocytes embedded within the matrix. They're connected to one another using small cytoplasmic processes within these small tunnels called canaliculi. So we can usually see the tunnels. We can't usually see the actual processes themselves. Okay? So the tunnels, you can think of it as a subway tunnel, is a canaliculus, and then the cytoplasmic process that passes through that tunnel, it's just the cytoplasmic process that attaches neighboring osteocytes as well as osteocytes to the osteoblasts out here. And so basically one of the jobs of the osteoblasts then will be to take nutrients and oxygen from the blood vessel and then pass it along to the osteocytes embedded within the matrix. Okay. Why? Why can't this stuff just diffuse across?
Has no water.
There's no water, or almost no water. Okay? So the matrix here is not hydrated, and so diffusion is not going to happen, which is why you need this transport through the cells. What kind of junctional complex do you think is connecting the osteocytes to each other? So at the end of the cytoplasmic process, these are junctional complexes. What connects them? Gap junctions. Good. So again, in epithelial cells, they're used to exchange information, and we find them again in bone cells as well. Again, used to exchange information, exchange waste, exchange nutrients, etc. Okay. All right, getting back to this. So again, you can see out here we have a fairly wide open tissue. There's really not much staining here. There's not many cells there. But if we look on this side, we can see very clearly there's a lot more cells. So there's an aggregation going on here. And again, so those will be the aggregated mesenchyme cells and osteoprogenitor cells. Again, they differentiate into these osteoblasts. And as these osteoblasts become embedded, you're going to need more osteoblasts. So this is why you have those osteoprogenitor cells to replenish those supplies. I like this slide because you can actually see the little wispy hairs of the actual collagen. So you can actually, if you look at the slide, you can see individual little collagen fibers sticking out in places. So you can see that, in fact, it's not a big, thick mass of stuff. They're individual fibers that are just very tightly packed together. Okay, let me just go back to this slide again. Look for some blood vessels. So there's one blood vessel over here. There's another one up here. There's another one somewhere over here, I think, as well. And if we take this a little bit further down the line, a little bit later on in development, we start to see these bone spicules kind of wrapping themselves around these blood vessels. So we have a blood vessel here. There's another one over here. There's one. There's probably another one up here somewhere. It's just off this slide. It's a bit of a longitudinal section for a blood vessel over here. Okay. So there are blood vessels all over this slide. And you can see that the bone tissue is kind of being laid down to surround these blood vessels. Okay, so let's switch back to the drawing. have this bone matrix being laid down to form this bone spicule. Periodically, osteocytes become embedded within it. What we're seeing is that the embedding of the osteocytes is kind of a fairly random process. So initially what we're really forming is something called woven bone, which Ortiz may have mentioned to you as well. Okay. Now woven bone tends to be fairly cellular, so it tends to have a lot of osteocytes embedded within it. And there's no particular pattern to how they are embedded. So we don't see the osteons that we would have normally associated with bone. Okay. So we've got a couple of spicules here. Let's fill in the osteocytes and osteoblasts. Oops. Again, always we're going to have that layer of osteoblasts on the surface of this matrix. Blood vessels here. Again. Sounds like someone was getting a phone call, or about to get a phone call. At least that's what my radio does. Whenever one of my neighbors is getting a phone call, it's to do a sort of beeping. There you go. So, here are, again, our blood vessels here. And so remember, as more and more matrix is being laid down, these bone spicules just keep on expanding. So I'm not going to draw the osteocytes this time because it's hard to keep track of them, but eventually they start to fuse together. Start to again wrap themselves around blood vessels. Okay, so here's again bone, and then on the outside of that always we're going to have lots of osteoblasts. At some point we might start to notice these multinucleated cells on the surface that might be basophilic nuclei that have an eosinophilic cytoplasm. And I'm going to use all the colors I have because I have them. And if you don't have pink, you don't have to use pink. Okay, so we will have some cells that might be more eosinophilic periodically. And again, these would be the osteoclasts. And at some point it might be useful to be able to do a little bit of bone remodeling. So this is why they will be present there. Now we all know that osteoclasts sit within a small depression within the bone, called a house shaped lacuna. That's right. We're almost there. That's good. Okay. So what happens there? Very rapid transport of protons into the region. So this cell is going to be secreting a lot of protons into the region. Okay, so kind of stick itself onto the surface of the bone. Okay, so let's kind of blow this region up a little bit. It's a bit of an aside, but let's just do it anyway. So here is our bone surface, the bone matrix. What we have is a osteoblast on the surface that kind of seals itself onto the surface and then has this kind of a ruffled edge on the inside. And then multiple nuclei. Now, why is this cell eosinophilic? Anybody ask for a TA? Anybody? Why is this cell eosinophilic? You don't have to color it, I'm just waiting for a response. So, why is it eosinophilic? Anybody? Going once, going twice. I think you said you knew everything about this stuff on last week. Eosinophilic because of the presence of a lot of mitochondria. Cells that are very rich in mitochondria tend to have a bit of an eosinophilic appearance to them. Why does this cell require a lot of mitochondria? Because it's very actively pumping protons across the membrane, and it's pumping them against the concentration gradient. Why does this membrane here at the base look so ruffled, with a ruffled border? Because there's very active transport going on there. So because of the constant secretion and absorption, it kind of looks like there is no continuous membrane in that particular region, because there's constant breakage of the membrane as things are dumped out of the cell and as things are being picked up out of the extracellular matrix. Okay? So why are the protons being secreted? So looking at H plus being pumped into this Kautschuk's lacuna. So why is there going to be protons?
Yes, creates an acidic environment for the enzymes to work at.
It's an environment for the enzymes to work at?
The acidic environment.
Acidic environment? Okay. Alright. Not necessarily about the environment. The enzymes are probably specialized to be able to work in that environment because of acidic. So it's not necessarily that it's creating that environment because the enzymes want to work in that environment. It's more that the environment's already going to be acidic, so enzymes have to be specialized to work in that environment. So yeah, you're probably right that the enzymes probably work fairly well at low pH, but that's not really why that pH is there. Why do we want to have an acidic environment in this region? What's in this matrix?
It's bone matrix, so we want to break down bone.
Right, we want to break down bone. So how do we break down bone?
Calcium uptake.
Calcium uptake, okay? So the acid is there to remove the calcium, to solubilize the calcium phosphate. Remember last week I showed you that bone that was bendable? It was soaked in acid for a couple of months. Well, in our case, in that case, it was soaked in acid for a couple of years actually. But it was that flexible after about a few weeks. Okay? I don't remember exactly the exact number of weeks. But basically, removing calcium exposes the organic component, and the organic component needs to be broken down by enzymes. Okay? Now those enzymes can't work unless they're actually going to be sitting in an aqueous environment. Right? So if you have no water, your enzymes aren't going to work. So you need to be able to introduce water into the region, so that means you've got to remove the calcium phosphate. Okay? So first of all, you got to demineralize the bone matrix, and then you got to chew it up with the enzymes. Okay? And so the acidification is the first step, is there to basically solubilize and remove that calcium phosphate. And so there's going to be absorption of calcium phosphate, and that calcium is then going to be dumped out here. Okay? So the calcium ions are going to be dumped outside of the cell, and this is how we can take calcium back into our bloodstream. Okay? So if we have low blood calcium, then that's going to be detected in your body, and there's going to be a hormone that's going to be released. The calcium is already in the bone. Okay? So the question is, how does it remove calcium? The calcium is already in the bone itself. It's in a crystallized form, which can't be easily taken out. What we need is a calcium form that is soluble. So what you do is make sure that it's in ionic form. Okay? And so what's going to happen here is that protons are being pumped actively into this space. Again, the cell has kind of sealed off this space, so basically there's a tight seal made around this area so that the protons don't escape. They're only being pumped into this region, which is why it kind of digs out a little hole around itself, and that's the high-shaped lacuna. And as the protons are being pumped here, they cause the breakdown of the calcium phosphate crystals. So the calcium can now become calcium ions, and we've got phosphate ions. Those will be taken up by the cells and then pumped back out here into whatever is outside of those cells. In the case of your bones, it would be into your bone marrow. In the case of here, where it's more going to be not as prominent, into the actual tissue, the matrix surrounding the mesenchyme tissue. Okay? And so again, in response to low blood calcium levels, calcium will be stripped from the bones. Okay? And so, remember we talked last week about osteoporosis a little bit? Okay? Basically, in your bones right now, what you have is a process of the laying down of more calcium by osteoblasts, and the removal of calcium from your bones by osteoclasts. Now, under normal conditions, this is a process that kind of is weighing basically fairly evenly. And so, as calcium is being deposited, it's being removed, and so it's a fairly constant sort of concentration or amount of calcium that's in your bones. Now, when osteoblasts become less active, and as in the case of osteoporosis, when you have fewer estrogen hormones or less growth hormone acting on those cells, or less testosterone, those cells become less active, they lay down less calcium in the bone matrix, but the osteoclasts are still removing that calcium at about the same rate. And that's how you're stripping your bones off their material and making them more brittle. So again, the trick is to lay down as much calcium as possible onto those bones to begin with while you're still young. This way you don't have as much of a problem with that as you get older. Okay, so basically we're releasing calcium by the actual... Okay, let's try that again. Let me turn down the volume a little bit more. Hopefully that takes care of it. I don't know. Alright. So, hold on there. Remember. Okay, so again, basically it's a balancing act in terms of the calcium amount. Okay? So let's get back to our description of intra-membranous ossification after all this. So now that you know how osteoclasts work, you can appreciate them a little bit more, I guess. Okay, so we start to have this idea of you've got individual spicules being produced, and as they grow, they start to merge with one another to make larger sort of structures. Okay? Remember, eventually what you want to do is make a fairly complete plate of bone, okay? A fairly continuous large sheet of bone. So you start out with small clusters of bone, and as they grow, they expand, they start to merge with one another to form a more continuous sort of sheet. Okay. By the way, how many of you again took anatomy last year or maybe this year? Okay, so you've looked at cranial bones, right? Have you noticed that where the bones, individual bones of the skull merge, they kind of have this interdigitation happening, where you kind of have like fingers. Okay, so I think we're safe for now. So again, this interdigitation occurs because these bones are kind of growing into one another as well. And so they kind of, as they merge, they kind of send out these dendrils so that they can actually fuse with one another and produce a more solid whole structure. Right? But how many of you have younger siblings? Maybe you remember those babies? Any chances are your parents told you not to touch the top of their head? Because you might hurt them? Yeah? Because those bones were still growing. Okay? They were still expanding. They didn't get to that point where you had a complete covering sheet on the outside of your brain, or their brain. Okay? So if you dropped your baby brother or sister at that point, you are the one responsible for how they are today. So it's your fault if you dropped them. They did not have a complete skull at that point yet, so they could not be protected properly. Right? So it's, your parents probably didn't trust you with the baby for a good reason. All right, so let's get back to our slides. Okay. So we have this growth of spicules as more osteoblasts being embedded, more and more expansion of these spicules. They eventually fuse together to make larger structures. Okay. And so again, we're forming this primary or woven bone. It's kind of a disorganized sort of fairly cellular sort of structure, which eventually will have to become replaced by more typical bone, or the compact and spongy bone that you guys are more familiar with from last week's lab. Okay? But initially it starts out as this kind of a woven bone, it's kind of a disorganized sort of matrix. Collagen was laid down in any direction that was possible. It's kind of haphazard arrangement. Whereas with the more mature bone, the arrangement of the collagen is much more highly organized. And again, this reorganization of tissue comes from the function of the osteoclasts, which are coming from the bloodstream, which is again another good reason to have the blood vessels involved. As you can see from this slide, again, we're a little bit further along now. And again, we have this fairly large bone trabecula here. And again, you can see it's spreading to envelop a few of these blood vessels. So you've got a blood vessel here, blood vessel here, blood vessel here, 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 here. I think I should move over here. So we've got a whole bunch of blood vessels. And you can see these growing out to envelop them. You eventually get to something like this. This is taken from the internet. I just steal this one from the internet because I didn't have a good picture of this. But it's a more mature form of what we just saw. Basically, down here, all these little red dots that you're seeing are blood vessels. They're small capillaries in cross-section. And you can see that around each one of them, we kind of have starting to see this organization of bone to surround it. Okay. At the outer edge here, we still have the development going on. So we still have up there, we can still see the aggregation of the mesenchyme cells and osteoblasts at the surface. Okay. But all of this is bone that has already enveloped a lot of this tissue out here along with the blood vessels. What's going to happen now? Well, have your TAs talked about how a conversion canal might be formed? Okay, let's talk about that. Okay, whether it's in this case here or in any case, whenever you're dealing with a bone matrix and you're forming a conversion canal, you're going to start out with, hopefully we'll talk about what the lamellae are, interstitial lamellae, for example. Hopefully that's somewhat familiar. Okay, so let's start with that. We've got some conversion systems to begin with. And we're going to have some osteoclasts cutting through that. Okay? So we're going to have basically what is called a cutting cone. If we were to look at it from the side, you'd have kind of a conical sort of structure going through bone. And on the surface, I guess I'm just going to use kind of a reddish marker, you're going to have osteoclasts. Okay, so I'm just drawing nuclear just so there's no, it doesn't look very sympathetic, does it? Okay, nuclear, blue color. So we've got osteoclasts. So we've got osteoclasts at the surface of this matrix. So again, you got to think of this in 3 dimensions. This drawing here is in cross section. This would be a longitudinal section. That wasn't me. Okay, so again, all of this out here bone matrix. So when this cutting cone goes through the bone, in cross section, what you would have is basically an opening that looks like this. Okay? And then around that opening, again, we've got the remnants of the old conversion system. So here are your, what will become interstitial lamellae. Okay. So this is the hole that would have been generated by this cutting cone. This again is a cross section. This is a longitudinal section. Okay. So just separate these from one another. Again, does everyone understand what's going on?
Why are these 2 circles in the first one?
Okay, so those are conversion systems. So it's a good question. Thank you. So this will be an osteon. So we're looking at it right here. Okay, so this is an osteon. And so those would be the concentric lamellae, so rounding those. Okay, so we have our concentric lamellae. Okay, so now what we have is an open space. Okay, that was opened up by these osteoclasts as they went through this bone. So what's going to happen? Well, in behind those osteoclasts is going to be a layer of osteoblasts. Again, they're going to be covering the surface of the bone matrix. They will be forming that endosteum. Okay. So this is osteoblast. And let's just go to this little osteoblast. Now, obviously, as you have osteoblasts there, they're going to start laying down some fresh bone matrix, and eventually they become embedded within it. So the further away you get from the cutting cone, the more likely you are to see something like this. Here's a layer of cells. And there's matrix covering them. And there's going to obviously be a layer of osteoblasts on the surface of this bone matrix. Now, what would this look like in cross section? Like this: osteocyte, osteocyte, osteocyte. and then a layer of bone matrix. Now, as we go further, again, further away from that cutting comb, we're going to have, again, another layer of these osteoblasts becoming embedded within the matrix. So again, more bone matrix laid down on top of them. And then again, more osteoblasts on the surface of that. Again, what would this look like? Again, osteocyte, 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 and then bone matrix on top. Okay. You repeat that a few more times, and it will start to look familiar, at least hopefully it will. And more cells embedded with the matrix, and becoming more cells. With the matrix, and then you have a central canal. Okay. And the center of this is what? Sorry, I didn't hear that. The central canal, what's inside the central canal? Blood vessels? Nerves. Which is why it really hurts when you break a bone. It really, really hurts when you break a bone. Because there's a lot of nerves there. Right? So what we've just drawn is the formation of a new osteon. So this right here is a new osteon. I keep on using this black marker for some reason. And so now the former osteon, or the lamellae of the former osteon that I just got chewed up partially, are the remnants. And these would make the interstitial lamellae. So these guys over here would be the interstitial lamellae that used to belong to some other osteon, but got chewed away in the process of bone remodeling. And so again, if you think of it this way, if we look back at this picture that we just saw, it's pretty clear that we have a fairly good idea of what's going to happen next. We've got a central blood vessel, and we've got the circular structure. We're going to have osteoblasts, probably osteoprogenitor cells in it right now, so osteoblasts eventually. What's going to happen? A layer of cells and bone matrix until you end up with this kind of a laminated structure. Okay? That concludes our intramembranous ossification, the formation of flat bones. Let us now move on to mitochondrial ossification, which I think is more exciting, but that's just me, because I like the colors. This is actually, incidentally, a picture I drew for my students when I was a TA in this course. I would basically spend hours before class drawing these things in big scale. And I learned very quickly to put up big signs saying do not erase. Because one day I came in after doing something like this, it took me hours to put it up. To come in the next morning to find out that's all been cleaned because our cleaning staff is so darn efficient. And so I learned very quickly that I need to start putting up signs, not to erase blackboards. In fact, they actually started setting up a system where now if you don't put any kind of erase marks on your blackboard, they won't erase it, they won't clean it. So if you want the blackboard clean, you actually have to kind of do a crappy job of just erasing parts of it so that they know that you don't care about what's on board and they can clean it. I'd like to think that I was part of that change. Yeah, so I still own a whole bunch of sidewalk chalk and colored chalk, so I used to put a lot of colors on my blackboards. And some students just started taking pictures of these things. I must just give you a CD-ROM full of photographs of my blackboards that he got one year. So that's where this picture comes from. And basically it describes the whole process. The process of endochondral ossification is very much a step-by-step process. It's very easy. You just have to know the right order of the steps. Okay? So if you want, you can just take a look at this picture, and we can walk through the whole process, or you can follow along through the actual text slides. And I think what I will do is, again, I think I will just simply go through a diagram with you guys so that you can draw your own diagram as we're going along. Okay? So, a lot of text on the next several slides. Again, it describes the process fairly completely. I probably won't be adding much to them, so you can just start drawing if you want. Most of the stuff that I'll be talking about probably will already be on the slides. So, first of all, endochondral ossification again starts during gestation. So again, in the fetus. This time around the 12th week of gestation when we start. And this time we're starting off with a cartilage template. So we actually start out with a cartilaginous skeleton, which gets converted into bone over time. And so this is a process that starts out in the fetus, but ends right around when you finish puberty. It differs from person to person when that happens, but by the time you're 25, it's done. You're not growing anymore. And your bones are your bones. There's not much cartilage left. Okay? And this is called epiphyseal closure. Okay? The process of just stopping this whole process is called epiphyseal closure. As I mentioned earlier, this is the process that produces what is known as the long bones of your body. And again, if you look at the actual terminology, endo refers to within, and chondro refers to cartilage. Okay, so you know the name of the process tells you exactly what's going on. It starts within the cartilage. Now, again, kind of like with the intramembranous ossification, you start out with mesenchyme tissue. So let's switch over to diagrams. And so again, we're starting out with, I'll draw them last time. I guess it doesn't really matter. So we're starting out with a bunch of mesenchyme cells kind of distributed randomly throughout the tissue. At some point they start to aggregate, so we have an aggregation of these cells together. But this time, they don't receive a signal to become osteoprogenitor cells. Instead, they differentiate into chondroblasts. Okay, so again, we have mesenchyme tissue. And we have aggregation. Okay, so what do you think is different about this process? We start out with mesenchyme tissue. We'll start out with aggregation of mesenchyme cells. What element I mentioned? What's different from this diagram, from the first one?
Instead of differentiating to osteoblasts, it goes to chondroblasts.
Right, but why? Why would they choose to go to chondroblasts as opposed to osteoblasts?
We don't have those local things.
Very good. There's no vascularization this time. It's possible that, maybe the lack of oxygen, maybe the amount of oxygen in the tissue might affect these stem cells to become a different cell type versus an osteoblast. So again, cartilage cells are not going to require vascularization. In fact, they effectively block it. So when they make the matrix itself contains factors that will block vascularization. Okay? And so that might be one of the factors, is the lack of blood vessels. And so we start out with a bunch of chondroblasts. Again, those are going to be on the surface of tissue. Okay, this time that tissue is going to be more basophilic. So we're going to have your cartilage tissue here. What type of collagen is this going to contain? Type 2, good. cells out here will be our chondroblasts. Obviously, as things progress, you're going to have chondroblasts that keep becoming embedded within the cartilage matrix. So you end up with chondrocytes, and then chondroblasts around the outside still. Now, what kind of growth can we expect to see within cartilage? Interstitial and depositional. Right? So, again, these chondrocytes are capable of division. This will become much more important later on. So, right now, what we're going to be seeing is mostly probably apositional growth. But what you end up with is basically a fairly small template for a bone. So let me kind of zoom out in the next diagram a little bit so that I can stop drawing cells. And we end up with a little bone. Okay. Or a little cartilage template for a bone. So there's a cartilage template. What kind of cartilage is this going to be? Yes. Hyaline cartilage, good. Okay. Now around the outside is going to be, eventually, what was the structure on the outside of this cartilage? What's it? Periosteum, good. So we have a perichondria. Perichondria. I must have misheard. Okay, so we have a perichondrium around the outside that contains the blood vessels as well as some of the mesenchyme cells that will be able to go ahead and replenish the chondroblasts as they are becoming embedded within the matrix. Now, over time, this template is going to grow to become longer and thicker. Okay, so let's make it bigger. And look more and more like the bone is supposed to form eventually. And again, there's constantly a perichondrium around the outside. So we have this fibrous material around the outside of this, which is going to be full of chondroblasts, and fibroblasts, and blood vessels, etc. So we'll just see where we are on the text slides. So at some point, what's going to happen is there's going to be a signal sent to the periosteum, and the periosteum around the diaphysis, so around this region right here, changes characteristics. And so instead of producing more chondroblasts, it starts producing osteoblasts instead. Okay? So what's going to happen here? Well, all of a sudden, right along the surface of this cartilage matrix, we end up with a bunch of osteoblasts that are going to start laying down what? Bone matrix. They're going to lay down osteoid, and they're going to start calcifying it. Okay, so we're starting to calcify the matrix around here. Why is that a problem? So let's say we're starting to calcify. Use a different marker. I'll try using green maybe, just to differentiate. So all of a sudden, it doesn't actually look green. It actually looks more purple. Maybe I should start using purple. Okay, there. Kind of a dirty purple now. Okay, so kind of visible. Okay. So we start this calcification of the matrix. What does that tell us? What's going to happen now? We calcified the matrix. What is the most immediate thing that's going to happen? What's the effect that we have? Yeah. Vascularization, you're getting ahead of me. Not quite there yet. Okay, so we're calcifying the matrix. Yeah. Okay, that's strength of the bone. Not quite yet. Okay. Remember, what's underneath that is cartilage matrix. Okay? Okay. What's the difference between cartilage matrix and bone matrix? It's going to be a weakening of the cartilage, but why is the question? Yeah. Is it kill the chondrocytes? Yes. But why? There's no diffusion. Very good. Okay. Difference between cartilage matrix and bone matrix. Water. Okay. Cartilage matrix is full of water. Bone matrix has very little. What does that mean? Well, it means that in cartilage matrix, you're going to have diffusion of things across the chondrocytes. If you calcify that matrix, there's no water. How are those chondrocytes going to get their nutrients? How are they going to get their oxygen? So yes, it will kill the chondrocytes. Okay? So it will start to kill the chondrocytes. If you kill the cell of the tissue, what's going to happen to the tissue? It weakens the tissue. There's nothing to maintain it, and so the tissue weakens. Okay? So right in this region here, we start to get to the point where this region here starts to really become weak. The tissue becomes weak. The chondrocytes here start to die because they're not getting any nutrients. Now, one of the other things that happens, and maybe I'll wait for it to get to it a little later, as the chondrocytes die, there's a very specific way in which they do this. They actually undergo apoptosis. One of the things that happens is that they lay down, I guess I might as well talk about it now, they lay down a hormone called vascular endothelial growth factor, or VEGF. I'm not going to get into the hormones too much, but this one is kind of relevant to us. Vascular endothelial growth factor. Based on the name, what do you think it promotes? Growth of blood vessels. Good. Endothelium, right? Vasculature. So it's promoting the growth of blood vessels. So as chondrocytes die, they start to lay down this hormone within the matrix. Okay. So what's going to happen next is that a blood vessel from the perichondria will be able to come in, break through this tissue, and basically spill its contents into the region. Okay. So what you end up with is basically kind of a cavity because the tissues become so weak that it's very easy to break through it. And so the cavity becomes filled with the material brought in by a blood vessel. What do you think that material is going to be? What's inside bones normally? Bone marrow. Good. Okay. So basically it's going to bring in bone marrow with it. Bone marrow contains RBCs. Okay, we're not too concerned with RBCs just now, but yes, it contains RBCs. What else does it contain? Bone marrow. What is your bone marrow responsible for?
Generation of red blood cells and white blood cells.
Generation of red blood cells. How does it do that?
Hematopoietic cells.
Hematopoietic cells, which are
Stem cells.
stem cells. Type of stem cell. Okay, so they bring in a lot of stem cells into the region. So those stem cells can become osteoblasts. What do you think is going to happen when those osteoblasts start settling right around here and right around here? Okay, so let me just maybe blow this up a little bit just so you get a better idea of what's going on. So let's take this image here and just zoom in. Okay, so let's take that image and zoom in. So here are my edges of the cartilage. And here's my damaged cartilage on this side. Here's my cartilage on this side. Okay. What we have out here is perichondrium. What we have in here, that shows a different color, is periosteum. In this region, we have matrix that has been calcified. And you will see on your slides that, in fact, calcified matrix seems to actually, in fact, be somewhat purple. Got a blood vessel coming in. Maybe I'll do it in pink just to differentiate it. So here's a blood vessel coming in. Bring in bone marrow. And so again, as we have osteoblasts out here on the surface, calcifying the matrix from the outside, so osteoblasts. Once we have the bone marrow within the actual marrow cavity, you can now have osteoblasts, and also they can migrate in from the periosteum as well, forming the endosteum on the inside. So you're going to have, just call it endosteum. Okay, which has osteoblasts within it. So you're going to have those osteoblasts up here as well, forming a layer of cells, and laying down fresh matrix and calcifying that matrix. So what's going to happen here? Again, more calcification. Of the cartilage matrix. It's happening up here as well. Calcifying matrix. Okay. Now, as this process is happening, the periosteum is also expanding up and down the length of the actual cartilage template. So that's spreading out, and so you're going to have more osteoblasts on the outside of this. And so they start to calcify this region as well. And so what you have is constant stress on the chondrocytes. Just put the chondrocytes randomly scattered throughout this template. Chondrocytes. So, this periosteum here is initially referred to as the periosteal bone collar. It's because, again, remember 3 dimensions. It's going to surround the whole structure all around that middle section. So, again, if we look at this bone up here, think of this in 3 dimensions. Right around the middle portion of that bone, you're going to have bone being laid down. That's periosteal bone collar. Okay, so again, as this cartilage is being calcified, it's being basically depleted of water, you're cutting off the supply for the chondrocytes that are closest to this region. And again, they become stressed, they start to undergo a certain set of changes. And again, one of those changes will be to calcify the matrix some more and lay down this VEGF. So again, that will promote more growth of the blood vessels from this region and the spread up into this region up here. So blood vessels will tend to want to go into this region as well. Okay. So again, imagine this process going on and continuing, and this region here just expanding. Okay? So this narrow cavity just keeps on getting bigger and bigger and bigger as bone is slowly replacing the cartilage. Now keep in mind that this doesn't become empty. Okay? What you're doing is you're simply laying down fresh bone, tissue. I guess I'll leave this one color. Okay, so you're laying down more fresh bone tissue over the surface of this calcified cartilage that's being broken down. And so we have osteoblasts on the surface of these, and eventually becoming embedded within them as well as osteocytes. And so it's not like this stuff is weakening, it's just being slowly replaced. So while the cavity might be spreading and become bigger, it doesn't mean that the bone becomes empty or the cartilage tissue becomes empty. It's still just slowly being replaced by a bone matrix instead of cartilage. So eventually all of this is not going to be filled with bone tissue. It's not going to be solid bone. But it's basically going to be replaced such that you still have the same sort of strength, if not more, but you simply have bone instead of cartilage. And by the way, why aren't our bones just solid bone matrix? Sorry? That's good. It would be too heavy. If your bones were completely filled with just bone matrix and there was no space within them for bone marrow, etc., you wouldn't be able to get out of bed. You wouldn't be able to move. Okay? So, sometimes you might feel that way anyway, but that's a different story. Right? So your bones are built the way they are. They have spongy bone on the inside, and again, they're mostly going to be spongy bone because this allows them to be light enough for us to move. If they were any heavier, we wouldn't be able to move. All right, so let's go back and try to catch up with some of these slides here. Hopefully everyone's kind of keeping up with the drawings. So we covered this. Okay. Again, calcification of the matrix, and so we have chondrocytes become hypertrophic. What does hypertrophy mean? Maybe define a couple of terms for you guys. Same thing that you guys have. I think I'm going to do this one or this one. So, the term hypertrophy. Let's throw in a couple of other ones. Hypotrophy. Very infrequently used term, this one, but more frequently used is atrophy. Probably heard atrophy before. What does atrophy mean? Shrinkage. So something that becomes smaller to non-existent. So shrinkage. This could refer to shrinkage in terms of cell size or shrinkage in terms of tissue or organ size. Okay. So for example, if you don't use your muscles, they will start to atrophy. They become smaller. Okay. That's what happens to people who, for example, are bedridden, or people who have an arm in a cast for a long time. Their muscles become smaller over time because they're not being used. And we'll talk about muscle next week, so you'll find out why. Okay. Hypertrophy is the increase in size. So when I say that a cell is hypertrophying, that means that it's becoming bigger. An organ like the heart, for example, can also hypertrophy. Okay? So it can increase in size. And I'm not talking about the bridge here, I'm talking about, in many cases, pathological sort of hypertrophy, where basically your heart is increasing in size when it's not really supposed to. People with heart failure tend to have that happen to them. The muscle increases in the size of it, and so the heart walls become thicker, but the heart's not really being as efficient as it should be, and so they have issues. There's also a more healthier type of hypertrophy in the heart, where if you're an athlete, for example, your ventricles might be thicker than most people's because you're used to pumping a much larger volume of blood and much faster. Okay? So there's different types of hypertrophy, but hypertrophy generally refers to increase in size. Okay? I guess if we're on the subject of some of this terminology, I'll throw a few more at you. Or not. Hyperplasia is an increase in number, usually referring to cell number. There's also going to be hypoplasia, as a decrease in cell number. Let's stop here. We're going to get into histology. Anyway, back to this. So the term here is the chondrocytes hypertrophy. So, as the cells are undergoing this process of apoptosis, the chondrocytes are undergoing apoptosis, you will see signs of hypertrophy. The cells increase in size. Okay? Now, in order to increase in size, remember, they are kind of stuck within this kind of a matrix that's pretty tough, pretty dense. That means they have to chew some of that away. Okay? So, they have to break down part of their matrix around themselves to make a bigger hole, a bigger lacuna, so that they can increase in size. Is that going to be important later? Yeah. Okay. And again, the weakening of the cartilage will lead to the death of the chondrocytes, and we just addressed why. Because there's no water in the calcified matrix, and so diffusion is not going to happen, and so they're going to run out of resources. And that's why. Okay. So we have an invasion of weakened cartilage. Okay. Hematopoietic stem cells come in along with our blood vessel, and they start the bone marrow development that we have within the bone itself. And that means we have an osteoblast that can be laid down. And also, remember, hematopoietic stem cells means monocytes, which means osteoclasts. Very good. Okay? Which means we can start to have bone remodeling. So we can have osteoclasts coming along, breaking down some of that calcified cartilage so it can be replaced completely by bone. So, this, as I mentioned earlier, this process basically starts to progress towards the ends or the epiphyses of the bone. At some point, you're going to have, let's move to this slide, something like this happening, where you have, initially again, just a regular cartilage sort of template. It grows in size and then starts to become calcified, as you can see the calcification going on right here. And then again, a blood vessel comes in and brings in bone marrow. And so all of this stuff that was here, all this cartilage that was here, becomes replaced by bone and bone marrow. But again, there's still cartilage at the ends. Okay? At some point, just before birth, one of these epiphyses is going to be also invaded by a blood vessel. And then sometime after birth, the other one will be invaded as well. So here's the terminology. This structure right here, this central region of ossification is referred to as the primary center of ossification. The regions that develop here and here at the epiphyses of the bones are the secondary centers of ossification. Now, the ossification that occurs here from the primary center of ossification is going to look a little different than the secondary center of ossification. So when you look at slides, you should be able to tell the difference fairly easily. And I will show you examples of that. Yes? So secondary centers of ossification will be developing up here. It's not on this slide yet. Okay? It hasn't quite started yet. Okay? But basically a blood vessel invades into this region, brings in bone marrow, etc. And again, the whole process starts in that region. That's the secondary center of ossification. And there will be another one over here eventually as well. So one of the centers of ossification starts just before birth. The other one happens after you're born. Yeah.
So secondly, it happens after.
So one of them will happen before, the other one will happen afterwards.
Is there a specific reason for why?
Is there a specific reason for why? I have no idea. It's a good question. I don't know. Probably just, we're too busy to do both at the same time. There's a lot of problems. Okay. So, I think I will just move on to diagrams again. But again, before I do, this is what one of these bones would look like with just the primary center of ossification. So what you're seeing here, basically a joint, this is the skin up here, epidermis, dermis, there's a bit of fat underneath that. And what we're seeing here is one bone, there's hyaline cartilage and articular cartilage right here. You can see a nice smooth surface going against this nice smooth surface over here. Okay, that's another bone coming into contact with it. So we have articular cartilages there. So again, this bone can articulate, it can actually bend, or not the bone bend, but the joint can bend. Okay. All of this here is hyaline cartilage. This eosinophilic material here is bone matrix. What I want you to notice is that there's a lot of this very purple, this very highly basophilic material in here as well, kind of embedded within that bone matrix, and that's the calcified cartilage. So, normal cartilage, calcified cartilage, bone. They have very different appearances. Okay? And again, this is the primary center of ossification. Out here, what we have is a periosteum. This region right here will still be classified as a perichondrium. And this region right here is still feeding this cartilage here. Okay, so let's go back to the drawing. So if we swing back to this right here, as I mentioned earlier, eventually we'll have a blood vessel invading into this region and into this region to form the secondary centers of ossification. This is secondary. Whereas this is the primary center of ossification. So now imagine this. Let's pretend you're the chondrocytes in this region right here. You have bone on one side, bone on the other. What do? You run, but there's no place to run. So this region right here is called the epiphyseal plate, or the growth plate. Remember when you were a kid, you experienced a growth spurt? This is where that was happening. Okay? So that epiphyseal plate is where that growth spurt was coming from. Why? Okay, let's take a look at this more closely. So first of all, let's just describe what it looks like histologically. Okay, so let's say up here, we have bone. I'm going to zoom in. Here is the bone from the secondary center of ossification. So here will be our secondary. So this region was where we would have our bone marrow. Let's draw a little bit of bone tissue here. So underneath that, we're going to have a cartilage tissue, a cartilage matrix. So here's just cartilage. Don't have to fill that in completely because we're going to put chondrocytes in there. Okay. So we're going to have a region within this cartilage that has relatively quiescent matrix, or really quiescent cells. These are just kind of randomly dispersed throughout this tissue. They're not too worried. They have a perichondrium out here. Let's make the perichondrium orange this time. I know it's a little inconsistent, but I don't have any different colors to work with. So we've got a perichondrium. And so these cells are quite happy as they are. Okay. Now, as we go towards the primary center of ossification, which is going to be down here off the slide, leave yourself some space. We will be drawing a whole bunch of zones in between this primary center and this cartilage that was just put. Okay, so at some point you will notice a pattern that kind of looks like this. You're going to have stacks of chondrocytes, one on top of the other. At some point, these stacks become a little bit larger. So the lacunae become bigger. I'm exaggerating things a little bit in this diagram. That's okay, you can do the same. Eventually, we end up with kind of remnants of these lacunae. It kind of looks like there used to be something that was connecting them more and more. And so you end up with these long strands of what is cartilage matrix going down to that primary center of ossification. Okay? And again, this is all matrix out here. again, in this region, chances are this matrix will look a bit more purple, a little bit more calcified, because it is more calcified. And at some point you will notice that there's a little bit of bone matrix on the surface of this. The bone matrix in red. That was very bloody. I don't know. Okay. So within the matrix, periodically you will notice some cells. So what's going on? Basically what we just drawn is the typical epiphyseal plate. So this is the region of cartilage that is stuck between that primary center of ossification and the secondary center of ossification. Now closest to the secondary center of ossification is a region of cartilage that is quiescent. This is just resting cartilage. It looked black to me, doesn't it? So resting cartilage. Some sources will just simply refer to it as just hyaline cartilage. At some point, you see kind of stacks of chondrocytes on top of one another. Now these chondrocytes are still normal looking chondrocytes. They have a nucleus, they have a little bit of basophilia. These are still quite active. What we're seeing here is that interstitial growth. We're seeing that division within the matrix. It's just that it's a very rapid division, and so these cells don't take much time before dividing again. And so this is why there's very little matrix material laid down in between them before dividing again. So these are cells that divide very rapidly, which is why they're stacked so close on top of one another. Okay, this is the zone of proliferation. Beneath the zone of proliferation is a zone of hypertrophy. This is where we start to see chondrocytes that are a little bit larger. They're starting to swell up a little bit. Some sources say that they can increase in size fairly substantially. I've read numbers like tenfold. So chondrocyte really increases in terms of its size and volume. Which means, again, if it's got a very small lacuna to begin with, it's got to chew away part of the lacuna, break it down a little bit, which again will weaken that cartilage. And so we have a zone of hypertrophy. This will increase in size. As they're doing this, they're basically activating the process of apoptosis. So they are becoming committed to cell death. They're starting to release They're starting to release vascular endothelial growth factor, or VEGF. They're also starting to produce some of those bone-specific proteins that I mentioned to you last week. Okay? So things like osteopontin and osteonectin will be secreted by these cells as well. Now, again, initially, when we first discovered these proteins, we thought they were bone specific, which is why they were given names that started with osteo. Well, it turns out that hypertrophying chondrocytes are capable of producing those proteins as well. Again, those proteins are there to hold on to things like calcium. Right? So they are there to help to calcify that matrix. And that's the other thing that these cells are starting to do. They start to calcify the matrix themselves. They're even producing enzymes like alkaline phosphatase, which is the enzyme that is responsible for producing that hydroxyapatite crystal in that ECM. And so they're starting to calcify that matrix, which is where we're going to start to see some of that difference in the coloration of that matrix when we start to get into that region. Right? It starts up in that region. And again, as the matrix becomes calcified, that means these cells are not getting food. They're starting to die. They've already activated the process of apoptosis, and so eventually we end up with kind of an empty lacuna with a little bit of garbage cell fragments somewhere within it, a shriveled up cell or something, or just an empty looking lacuna, and that's what we see in the zone of cell death. Now, just before we get to that point, though, I guess I probably should have drawn this a little bit differently. These hypertrophied cells will show a nucleus that is very large and very pale. Okay. Let's slow down. This pale nucleus is a sign that you're reaching the zone of cell death. Basically means that the chromatin inside of that nucleus is being degraded. And so there's nothing left in the nucleus to pick up any stain. Okay? What we're looking at here is something called karyolysis, or the lysis, the breakdown of the nuclear material. Karya refers to nucleus. Prokaryotes, eukaryotes. Karyo refers to nucleus. And so karyolysis is the destruction of the contents of that nucleus. And that's what you're seeing here when you're seeing these pale solid nuclei. And then beyond that, you're going to see either empty lacunae or one with a little bit of shriveled up cellular material within them. So it's a zone of cell death. And then you have the zone of resorption. After that, we've got bone. Okay, so this structure right here, where you have some purple material and some bone matrix on the surface of that, would be referred to as a mixed spiculum. Okay. And so initially what you have is this cartilage matrix here basically acting, these little bits of cartilage matrix that were between these rows of cells remains. And that's acting as a scaffolding on which the osteocytes can come along and lay down fresh bone matrix. But if you want to have a mature bone, you don't want to have calcified cartilage within it because calcified cartilage is brittle. And so what you want to do is eventually want to replace all that calcified matrix with, or calcified cartilage matrix with actual bone matrix. Okay? And so what you're going to have is a constant turnover where there's going to be bone being laid down on one side of this, and there might be an osteoclast on the other side, and maybe breaking it down from the other end. So that what we end up with is a breakdown of this calcified matrix and a laying down of fresh bone matrix on the other side. Okay, so is everyone following the diagram? Okay, let's go to the actual images so you can actually see what's going on with the pictures. Let me see what I take this. But this picture here is actually showing you the primary and secondary centers of ossification. Okay? So we've got the bone here, this is the end of it. Here's the surface, this is the articular cartilage. Okay? This is a secondary center of ossification. You can see this kind of a spongy bone, and then we have this cartilage around it. Here's the epiphyseal plate, and here's the primary center of ossification. Same thing, but this time under the microscope or colored. And so what we're looking at here again is up here would be your articular cartilage, secondary center of ossification, primary center of ossification would be down here somewhere in the corner. Okay? So you can see that the two of them look very different. This looks very quiet, and there's not a lot going on here at this point. Okay? Just kind of bone develops and then kind of stops. And the cartilage up here is kind of safe. It's not going to be destroyed any further. Okay? This cartilage up here doesn't really have anything to worry about from this direction. It's all coming in from this direction. So the development of bone is coming in from the right-hand side here. And so let's zoom in on our region here. Before we do, I told you guys you'll be seeing this slide again this week. Okay? So last week we saw this. Up here is hyaline cartilage. This will be the perichondria. I want you to notice that down here, there's a slight difference in how the chondrocytes are organized. Okay? So perichondrocytes are kind of haphazardly kind of laid out. They're not really organized in any particular way. There's kind of a random distribution of these things. Down here, we're starting to see a bit of a stacking of the cells. The mesogenic groups are starting to become a little bit more elongated. We're going to go a little bit further down within this, and this is the same slide, we just kind of turned it a little bit and zoomed in on it. So if we go back, this region right here is this region right here. Okay? Now, this is a bone developing before that secondary center of ossification, so there still is no epiphyseal plate. But we're starting to also see a very similar pattern. We're starting to see a stacking of chondrocytes. Right? So we're seeing a zone of proliferation. In this region here, we're starting to see the lacunae become much larger and the chondrocytes become larger, so we're starting to see hypertrophy here. The characteristics of the matrix change a little bit here as well, so it's starting to get calcified. Eventually, we have these empty spaces here, and it's actually not that empty because there's an osteoclast in here. But basically what we have are these kind of long projections of this cartilage matrix that are left over that will then be built upon by the osteoclasts, which will become embedded, become osteocytes. We're going to have osteoclasts in here. There's one over here, there's one here, there's one here, now there as well. Again, there was an osteoclast in well, it doesn't really look like an osteoclast that much. There's a lot of them. And all of this out here, by the way, this is bone marrow. Okay, so all these red dots that you're seeing here are some of those hematopoietic stem cells that are going to be developing into things like red blood cells, etc. Okay. So let's take a look at the pictures, because basically what's the text that's on there we've already described. So again, this is our developing bone. We've got a secondary center of ossification, primary center down here, and right down the middle what we have is that epiphyseal plate. Now this bone is fairly far along, so that zone of resting cartilage is not very pronounced here. If you look carefully, you'll see it over here roughly. That's still a zone of resting cartilage. But up here, there is no resting cartilage anymore. That epiphyseal plate is very close to epiphyseal closure. So this bone is almost done developing. Okay? So let's take a look at this region right here in a little bit more detail. But before we do, notice again, very, very basophilic region, cartilage matrix. As we go towards the right, we start to see these streaks of this basophilic material within the actual bone matrix material. Those streaks are those septa of the cartilage matrix, the calcified cartilage matrix. So let's again take a look at this diagram here. This right here will be that cartilage matrix, that's kind of fairly thin septum that is in between these stacks of cells. The fact that these cells died here and they enlarged their lacunae has weakened this region, and so there's a very thin bit of cartilage matrix that can be very easily broken through by a blood vessel. And so these can be very easily invaded, these long columns can be very easily invaded by blood vessels and osteoblasts and osteoclasts. What remains are these long septa of calcified cartilage that basically are being used as templates to lay down fresh bone matrix on the surface, and that's what we're seeing within that picture. So if you look here, you've got these very long projections. These are the remnants of that set of those septa that would have formed in between individual chondrocytes in the different rows. And that's what you're seeing here. And again, you can see that they're embedded within the bone matrix. And the further to the right we go, the less and less of that we see, and more we see of, a bit more mature looking bone. It's just bone matrix by itself, as opposed to with a bunch of cartilage embedded within it. So that is the aim of this whole process, is to replace as much of this cartilage matrix with bone matrix as possible. So in the end, you end up with just bone matrix with no cartilage at all. So let's zoom in a little bit. And so at this point, we're basically looking at from the top down. So kind of like our drawing that you just did. This is what we're looking at here, except again, we don't have that quiescent cartilage anymore. Okay? And so what you're seeing at the top are these stacks. And again, these lines going across are just artifact of preparation, so don't worry about those. But if you look carefully, you'll see just stacks of chondrocytes, one on top of the other, kind of like stacked plates. Okay? That's the zone of proliferation. So we have chondrocytes dividing rapidly. They don't really have much time. You can think of them as trying to get away from the area of calcification. They're trying to run away by just dividing and running away from it, and just getting away from it in that way. And as we get a little further down, we start to see that some of these are starting to round up a little bit. They start to become a little bit bigger. So we're starting to see a zone of hypertrophy. And as you get deeper and deeper, you start to notice that some of these hypertrophy chondrocytes have a very pale nucleus. So in this region, we're probably looking at cell death. The DNA within those nuclears is starting to get chewed up, and so we have basically no chromatin left to actually pick up methoxylin. And so we're seeing this kind of an empty-looking space. So up here, zone of hypertrophy. Down here, you can start to see it here as well, kind of a shriveled up looking cell, zone of cell death. Yeah?
So at 25, it changed, by 25, everything changes to bone now?
So by the time you're 25, you don't have this anymore. This is all bone. Okay? So you guys probably would have seen some of those cut open femurs that we have in the labs. Did you guys get a chance to look at the femur? Because in the labs, there should be a bone that's been split in half down the side. So you can actually see inside of it to see what spongy bone looks like versus compact bone. But if you look on one of those epiphyses, you can actually see the actual epiphyseal plate, the actual closure, the fusion line, because you can see where everything kind of just merges together to this kind of fairly solid looking line across the surface of that. So do look for that in the labs. Okay? But yeah, by the time your puberty is done, by the time you stop growing, basically, this is all replaced by bone. Okay? And so what you're seeing down here at the bottom is the invasion of blood vessels into these long columns that used to be occupied by the chondrocytes. And so what you're seeing is these darker lines in between. Those are the septa of that calcified cartilage that are going to be acting as the templates for the laying down of bone tissue. Yeah?
So I was just wondering, you have this zone of proliferation and zone of hypertrophy.
Yep.
And presumably, cells from the zone of proliferation turn into hypertrophy.
Right. So eventually they will hypertrophy and they will die.
They're separated by a fairly short distance. So what type of signal makes one cell,
So what type of signal
would make a cell
would make them go from this to this?
Yeah.
Well, the calcification, first of all. Again, there's going to be localized signals that will be sent to these cells to induce them to do certain things. Okay? I don't really want to get into the nitty-gritty of all the different hormones and signaling molecules that are involved, because it's not really the point of this course. But there's a variety of signaling molecules that will be sent to these cells, and these cells might start expressing different cell surface receptors so that they can become sensitive to certain molecules as well. Okay? So depending on which region they're in, they're going to have slightly different surface receptors, and they will have sensitivities to different molecules. Okay? But again, I think it's beyond the scope of this course, and I can't keep all that stuff straight in my head anyway, so I won't even attempt to describe all of that stuff. Yeah?
Why is there a difference between the secondary and primary influence on that? Why would it not go the other way, so it starts stacking down?
That's a good question. So the question is, why doesn't it stack in the other direction as well from the secondary center calcification, right? Again, it has to do with the signaling molecules and how they're being distributed to the cells within the cartilage. Right? So again, I don't know the specifics, I can't really speak to the specifics, but basically it has to do with how the signaling molecules within the matrix are being maintained. Okay? So again, that cartilage matrix, that ground substance, even though it might not seem like a big deal, it actually is a very big deal. The ECM within these tissues is extremely important for this whole process. Again, there's going to be different types of molecules within that will regulate the activity of all these cells. Okay? let's move on to the next one. Again, we've kind of turned it sideways now from the previous slide. We're just going a little bit deeper in. And so at this edge here on the left-hand side is where we would have seen that zone of bone or matrix resorption and laying down of fresh bones. So you can still see some basophilic regions here. And then you can start to see some of these septa are becoming embedded within bone matrix. And the deeper we go, the more bone matrix we see over the surface of these. And again, if you look around, you can see a variety of cells, including osteoclasts, that will be breaking down some of this matrix material so that it can be replaced completely by cartilage. If you're wondering what this is just a blood vessel. So you can see red blood cells within it. This orange-colored material is red blood cells. Okay, so we'll stop here and pick it up again next week with the